Okay, so for our physics units, okay, the important things in physics is what we'll go over. I'll talk about whether they're going to be in the multiple choice or written response, problem solving types of things, okay, details, stuff like that. One thing I'll tell you right now, there were a lot of people and places and dates in that first lesson, and they're pretty minor, okay? Like I really wouldn't spend time going over who Orsted and Joule and those kind of people were. Okay, it's just not that important. Okay, make sure that you are able to demonstrate your skills, okay, to do with physics and know the energy types and systems and all of that kind of stuff. All right, so first thing we went over were the types of energy that is going to be tested in the multiple choice. All right, so that's all kinds of things like solar energy, chemical energy, electrical, magnetic, mechanical, potential, kinetic, okay, all of that kind of stuff. Okay, all of those are the types of energy. Okay, so make sure you're able to identify those from a description in a multiple choice item. Okay, so just be able to again, like I was saying, generally recognize, okay, an energy type. Like, if I think on your unit exam, the example was a bowling ball. What type of energy does a bowling ball have? And you could have said kinetic or mechanical. Okay, whereas a tank of propane would have, okay, potential or chemical, okay, something like that. All right, so types of energy. Thermodynamics, okay, was the thing that came next. We had two laws of thermodynamics that we went over. The first law is the law of conservation of energy. Okay, energy can't be created, it can't be destroyed, it can be transferred, it can be converted, okay, all of those kinds of things, but it will always be there. Okay, and then obviously the second law, okay, second law talks about the direction of heat flow. Energy always flows from high to low or hot to cold. Okay, so make sure that we understand that. There could be some multiple choice questions that get fairly deep on that stuff, okay, like possibly things about why a perpetual motion machine can exist based on the laws of thermodynamics, or how a heat pump works, or things like that. Things that we talked about. Okay, it won't be anything that's new, right? But it will be things that we did talk about in class. Okay, so hot to cold, high to low. Okay, like we were saying here. Okay, and then talk about again heat engines and heat pumps. Okay, those. Okay, a heat engine uses the second law of thermodynamics, but a heat pump goes against it, uses energy and pumps hot air into the already hot area. Right, so again, all that stuff is multiple choice. Okay, all of that stuff will be tested in multiple choice. Okay, and so something here, systems, need to know those. Okay, so we had open, closed, and isolated. Okay, remember, open will exchange matter and energy. Okay, closed will exchange energy. Isolated doesn't exchange either one. All right, then we went into scalar and vector quantities. There may be a multiple choice question, which of the following is a vector quantity, something like that. But most of the marks to do with scalar and vector quantities are going to be in the written response and in this way. You get a physics question, maybe it's a graph, maybe it's an acceleration problem or something like that, and it asks for, what's the total displacement of the object? Is displacement a vector quantity? It is. So do you need to put a direction on it? You do. Okay. If you recall, that happened on one of our acceleration problems on the unit exam. Okay. Well, just about everybody forgot to put a direction on the velocity, the final velocity for the acceleration problem. Okay. So that's one of the places where it really makes a difference. But the other place where it really makes a difference is in any graphing questions. Okay, we solve for distance differently than we solve for displacement on a position time graph. Okay, we solve for acceleration. Okay, it's a vector quantity. We need to have a positive or a negative or a north or a south or something like that on it. Okay, you don't want to lose marks needlessly after having done a question entirely right and then forget to put a vector on the answer and lose a mark. Okay, so make sure that you have that you're recognizing which things are vector and which things are scalar. Okay. All right. Along with that, okay, we did some v equals d over t problems. Don't expect to get any like 5-mark v equals d over t problems in the written response of your final, but you could get a simple one in the multiple choice. Okay. Are there times where you might use v equals d over t in a graphing situation? Yes. Okay. If you had a position versus time graph that wasn't a single line, okay, and you might have to use it then. All right. So if it had a bunch of different sections, then you might use v equals d over t for that. Okay. So remember displacement, okay, final position minus initial position, all that stuff is on the formula sheet, but just remember that that's going to come up a fair amount, okay, especially if you've got a position versus time graph on your final exam. Maybe. Okay, it's one of the ones you have to use there. Okay, then acceleration. Okay, expect that you're going to get a written response problem that is based on acceleration, a equals vf minus vi over t. Right, that's also a formula that may end up getting used on a velocity versus time graph question. Okay, if you were to get one of those, it may come up there as well. Okay. I wouldn't expect it to be much different than any of the ones you did in class, okay, or the one that was on your unit exam. Okay, I gave you acceleration, I gave you initial velocity and time, and you had to calculate final velocity. Right. Okay, graphing. There's a fair amount of graphing on the final. Okay, if there's one thing in the physics unit that's worth, kind of more marks, okay, it would be like work energy theorem and then graphing. So there's some graphing questions in the multiple choice and the written response. The ones in the multiple choice are more reading and interpreting. So I look at this graph and I'm asked to say what's going on in this graph, or something simple like, what's the slope of the line or something like that. Okay. In the written response, there could also be some reading and interpreting. Like I could give you a question where you have a graph that looks like this, for example. Okay, and it's, let's say, a position versus time graph. Okay, and then I would label it like A, B, and C, and I might ask you, what is the object doing in part A? All right, what is that object doing? Nothing. Its position is not changing, therefore it's not moving. Okay, in part B, it's moving backwards at a constant velocity, and in part C, it's moving backwards at a constant velocity that is slower than B. Okay, something like that, just describing, but be thorough, right? If you just say moving, that's not going to get you the marks. Okay, make sure you're mentioning things like direction, okay, stuff like that. So reading and interpreting, okay, definitely part of the graphing stuff. And then extrapolate, okay, you're going to be asked to use y equals mx plus b. One of the graphs will be linear, right? And I would put the equation on that line and ask you to calculate things like, what will y be when x is this? Or what will x be when y is this? Okay, what's the slope of the line or whatever? Okay, things like that, okay, are going to definitely be on there. Okay, so make sure you do that. Remember that, and because this burned a bunch of people on the exam. If the question says, using your graph, use the graph. Do not use other formulas. If it says using the graph, it wants you to use the equation for the graph. Okay, what got people on the unit exam was they didn't use the graphing equation and didn't take the y-intercept into account when they did their calculations, and as a result, got the wrong answer. Okay, everybody follow me there? Right, it was a position versus time graph, and people just went, oh, well, v equals d over t, and did that calculation, when in actual fact, v was y minus b over t, and they forgot about this part. It's not the same, and they didn't get the same answer because they forgot to take that initial position, the y-intercept, off. okay, when they did their calculation. So if it says using your graph, make sure you use the equation for the line on the graph. Okay. So remember, position versus time graphs. Okay, there'll be one position versus time, one velocity versus time graph. Okay, these are the formulas that we got off of there, right? So if I have a graph, a position versus time graph that looks like this, right, and I'm asked to calculate the average velocity, can I use this? Nope, because I have many sections here, right? I don't have one best fit line on that graph. So in this case, I would have to figure out, okay, what's my final position here minus my initial position divided by time. That would give me the average velocity there. On this graph, yes, I could use y equals mx plus b because it's one line, and that equation would probably be attached to the graph. Okay, also remember that, okay, again, the slope of the line on that graph is speed, is velocity, because it's y minus b is final position minus initial position, x is time. Okay, that's how we calculate time. That's where we get that formula from. Right, and then for our velocity, okay, for our velocity versus time graphs, okay, remember that we can calculate acceleration from the slope, okay, because that's this formula here. If I go y minus b over x on a velocity versus time graph, that's vf minus vi divided by t, okay, that's what it's going to be calculating. If I got a graph that looked like this that wanted the acceleration, then I would use the formula, okay, because I don't have a single line. Everybody all right with that? How do I calculate the displacement on this graph? The shapes, yeah. I find the area underneath the line, right? So I'd have like this rectangle, this triangle, and this rectangle. Okay, I calculate their areas. That's average velocity times time, getting me the displacement of the object. Okay, so things like that are going to be worth practicing. You have a bunch of, and I had another example of it here. Okay, you have a bunch of practice problems on that stuff on your worksheets. Okay, and there's also on the final exam review that I gave you, the last two questions I think are graphing. Okay, and there's graphs there that you can practice with. Right, so just remember that's how we do that. If I had a graph that looked like this, okay, the area of this rectangle here would be 3 times 2 is 6. Okay, the area of this rectangle here would be 3 times 8, okay, which is 24. Right, this one here is going to be 4 times 6, which is 24, and so on. And we just add them all together. Okay. Questions on that? Is that ringing a bell? Okay. All right, after graphing, then we did work energy theorem, which is the most important concept in that unit. So expect that you're going to get at least one, if not two, work energy theorem problems in the written response of your final exam. But there will also be some multiple choice questions about work energy theorem, okay, just about the principles of it. Okay, what's work? Work's a change in energy. It's a change in mechanical energy, right? What's kinetic energy? What's potential energy? That kind of stuff. Okay, so there'll be some checking your understanding questions in the multiple choice, and then there's going to be, okay, some written response items that involve work is force times distance, and it's a change in mechanical energy. Okay, so remember that means work equals EF minus EI, or force times distance equals EF minus EI. Okay, all of these, these formulas here are on your formula sheet, okay, it's for potential energy and kinetic energy. How do we calculate mechanical energy? Right, okay, mechanical energy, which is what this and this are, is the sum total of both the kinetic and potential energy of the object. Okay, questions on that? All right, we did a bunch of those, and those actually went pretty good on the unit exam, so we just want to make sure that we still understand how those work. Okay, and then conservation of mechanical energy, roller coaster questions, or toboggan going down a hill, or person jumping out of a plane, or whatever, okay, where only gravity, no friction, okay, is acting, and we're converting all the initial mechanical energy into final mechanical energy, or EI equals EF. Okay, so if we had an example like this one here, okay, maybe we'll just walk through this one. So I have a 20 kilogram block, and it's at the top of this 20-meter high hill, and I want to calculate how high above the bottom of the hill it is when it's moving at 10 meters per second instead. All right, so in that case, EI would equal EF, okay, which would mean M times G times H initial plus 1/2 MV initial squared equals 1/2 MVF squared plus M times G times H final. All right, what am I looking for in this question? HF, I'm looking for the final height. All right, so I need to get that by itself. So I'm going to subtract this over to this side, and I'm going to cancel all the m's because I don't need them. All right, so I'm going to have GHI plus 1/2 VI squared minus 1/2 VF squared equals GHF. Then I'm just going to divide both sides by G. Okay, find my HF. All right, plug in my numbers. So 9.81 times 20 plus 1/2 times 4 squared minus 1/2 times 10 squared divided by 9.81. Okay. That'll give me my final height. All right, so the final height is going to be 15.7 meters. All right, so expect that you will see one like that in the written response on your final exam as well. All right, and then after that, we just briefly talked about efficiency. Okay, so that's what we just did there. Okay, we briefly talked about efficiency. It's just a multiple choice question about efficiency. Okay, the work in divided, or sorry, the work out divided by the work in gives you the percentage. Okay, so the work that actually gets done divided by the energy you actually had to use, and it gives you the percentage of the actual work being done. Okay. Questions from you guys? Anything you want me to go over in more detail, demonstrate, re-explain? Okay, why don't you try that one? Work energy theorem problem. Okay, what force is used to throw a ball whose mass is 1.5 kilograms over a 1.5 meter distance to a height of 15 meters? Or sorry, 21 meters, not 15 meters, 21 meters. Okay. Give you a couple minutes on that one, then I'll walk you through it. All right, so with any work energy theorem question, the first thing we have to do is decide what kind of energy is being changed. Okay? In this case, we're seeing that there's a change in height because it's asking us how much force is being used to throw it to a height of 21 meters. Height has to do with kinetic or potential? Potential. All right, so in this question, work is changing the potential energy of the ball. Okay, so we've got force times distance equals, okay, the final potential minus the initial potential. Where am I to assume I am throwing this from? From the ground where the height is 0. All right, so do I have any initial potential energy? No. So I can take that right off. So what I'm left with is this. Force times distance equals m times g times h final, and they want me to find the force. So what do I do with distance? Divide it over to the other side. Okay, that'll calculate my force. So I'll take 1 1.5 kilograms times 9.81 times 21 meters, and divide that by 1.5 meters. All right, so 1.5 times 9.81 times 21 divided by 1.5. So 206 meters. It's pretty high. I don't know if anyone actually throws. Sorry, 206 newtons. Sorry, that's reasonable. 206 newtons is the force being used to throw the ball. Okay, everybody all right with that? Okay, so all work energy theorem problems work that way. Identify the type, set work equal to the change in that type, and then manipulate for whatever it is you're looking for. All right, let's have you guys try that one. So same steps as the last one. We have to identify what type of energy is being changed. In this case, it's kinetic energy because the speed is changing in this one. All right, so we've got that work equals the change in kinetic energy here. All right, so that'll mean that we have force times distance equals the final kinetic, 1/2 mvf squared, minus the initial kinetic, 1/2 mvi squared, except that we're starting from rest, so vi is 0, right? Which means we have no initial kinetic energy, right? So if we are looking for, we're looking for the final speed, so we're looking for vf, so I divide both sides by 1/2 of m, and then I square root, okay? That'll give me vf, so that'll be the square root of 500 newtons times 15 meters divided by 1/2 times 1,000. Okay, so end up being 3.9 meters per second. Okay, questions on how that one works? Okay. Whoa. Okay, so if I give you a position versus time graph that looks like this, all right, the things I might ask you to do would be, let's have a part A and a part B here. So part A would be, where will the object be at 20 seconds? Okay, and part B could be, okay, how long to reach a position of 80 meters? This is exactly what I asked you to do on your unit exam. And I also asked you, what was the velocity of the object? Right? What's the velocity of this object? 4.5 meters per second. Remember, the slope of the line on this one represents the velocity. Okay, see if you can calculate A and B here. Okay. All right, so for part A, it's asking where the object will be. So am I looking for a y value or an x value? A y, because position is on the y-axis. Where you are is your position. So, okay, we're looking for a y value here. The good news about that is I don't have to manipulate the equation. It's already set up to solve for y. So all I have to do then is go 4.5 times 20 seconds. Okay, that'll be our x plus 6. So 4.5 times 20 is going to be 90 plus 6, so it'll be 96 meters, right? Okay, that'll be my position. Now, for B, it's asking me how long to reach a position of 80 meters. So this time they gave me a position. That's a y value. I'm looking for x. X is time, right? So I'm looking for x. So when I manipulate, okay, x will be y minus b over m. So that'll be 80 minus 6 divided by 4.5. Okay, so 74 divided by 4.5. Right, so it'll take 16.4 seconds for it to do that. All right, ringing a bell for everybody. All right, I'm just putting questions up here. You guys didn't have any. I'm just trying to show you kind of some of the things I'm going to ask on the final here. Okay. Oh, precipitates, right? We forgot to talk about that the other day. All right, just as a quick review for chemistry, solubility. Okay, when we were talking about solubility terminology, okay, there was like, you know, solute, solvent, and then we had precipitates. Okay, and we could determine whether something was going to be a precipitate or not by looking at our periodic table. Okay, because we had that solubility chart on the periodic table. Okay, and it's on the back here. All right, so in this reaction here, I have sodium iodide. It's reacting with lead 2 nitrate. It's forming lead 2 iodide and sodium nitrate. Question could be like a multiple choice question, and it would say which of the products, or which product or products are soluble. Okay, so if I go to my solubility chart, okay, I look up for iodine. Okay, so iodine is right here. Okay, it says it's soluble with most things, but not with copper, silver, mercury, or lead 2. All right, so that one's a precipitate. It's not soluble. Since the question asked which product is soluble, I've got to check and make sure that sodium nitrate is soluble. All right, so nitrate soluble with most things, but not with these big long things. But it is soluble with then sodium. So sodium nitrate would be soluble. All right, everybody kind of follow on that? I forgot to review that when we did the chemistry part. Okay. I think that was, oh. All right, try this one. It's an acceleration problem, okay? Very similar to what I asked on the unit exam. So there's kind of 2 tricks in this one. First off, if something falls, what's its initial velocity? 0, right? I didn't throw it, okay? It wasn't projected, it was just essentially dropped, falling and being dropped are the same thing. So VI is 0, and I have to assume that this is happening on Earth, where acceleration is 9.81 meters per second squared. Right? So it's possible for a question to do that. It gives you information, but doesn't outright give it to you. Right? So we are looking for the final speed of the nail. Right? So we've got A equals VF minus VI over T. Okay. It says how fast. That's how I know it's speed, because it didn't say how fast and in what direction or final velocity. Right. So I'm going to multiply both sides by T, and then I could add VI, but is there a point? VI is what? 0 anyway. Okay. So A times T will equal VF in this case. So 3.5 times 9.81, and I've got my answer. Okay, so 34.3 meters. Sorry, meters per second is the final speed. Okay, questions on that one? Okay, that's what I've got for you in terms of physics review. Okay, give you guys some time here. If you come up with some more questions, feel free to ask. I'll put the review thing back up on the board. There's some really good physics questions in that, especially the graphing ones. Oh, where did I put them? Oh, sorry, the graphing ones are in your unit exam review. That's where they are. Okay, so there's some graphing questions in the unit exam review package that would be worth going over. I do not have any in the final exam review, okay? But make sure that you go over the ones that are in your unit exam review, okay? Because they were good and the answers were on there for them.